So in the last week, we actually saw about conventional sets, the operational operations on conventional sets, and then we moved on to an introduction of fuzzy sets. We saw the formal definition of fuzzy sets, and we also discussed the types of universes which are there with respect to fuzzy set. So we'll continue with this and we'll see some other concepts which are related to fuzzy sets. So the outline for today's lecture is we look at different notations for representing fuzzy sets. We will be looking at linguistic variables and values. We'll see what these terms mean actually in the context of a fuzzy set. Then some more terminologies with respect to fuzzy sets we'll be looking at. Then we'll be looking at the standard operations and the properties of fuzzy sets. So we have seen one particular notation for representing a fuzzy set, and that is using ordered pairs. So there are several such notations. So let us get ourselves familiarized with these notations. So first is using ordered pairs. Next we have using membership functions, both mathematically and graphically. Next you have using the plus separator notation. We'll look at examples of these one by one. So first is using ordered pairs, which you have already seen. So this is the way you write or represent a fuzzy set using ordered pairs. So you have the element followed by the membership of that element into parentheses, and these are separated by commas. So for example, if you want to represent this particular scenario using the ordered pairs notation, okay, so the question is, there is a realtor who wants to classify the houses, and the indicator for comfort for these houses is the number of bedrooms. Okay. And you have to represent this as a fuzzy set, to create a fuzzy set which represents this scenario. So basically, this is the universe of discourse. So the kind of houses that he has these number of bedrooms starting from 1 to 10. And the you have to model a fuzzy set for a 4-person family. So a comfortable house for a 4-person family. Basically, this is the fuzzy set that you have to model. Comfortable house for a 4-person family. So using the ordered pairs notation, how will you model this? Whenever you are modeling a fuzzy set, first thing is you have to define the universe of discourse, and then depending on whatever is written here, you have to decide what will be the membership of each of these elements in your fuzzy set. Right? So 4-person panel. Right? So we can say that if the house is having 4 bedrooms, then that particular house is comfortable enough for a 4-person family. Okay, so understand that each of these is representing the number of bedrooms, right? So what will be the comfort? I mean, what will be the membership of these elements? So if it is 4, if the house is having 4 bedrooms, then in that case it will be very comfortable. If the house is having 3 bedrooms, then also you can say it is okay, quite comfortable. Okay, so you can say 3, 4 is having a membership of 1. Okay, And then you have to decide. So as the number of bedrooms increase, maybe 3, 4, 5 is having membership of one, or only 4, 5 is having membership one, or only 4 is having membership one. That is subjective. Okay? But as it decreases, it becomes less comfortable. The space is less, right? And as it increases also, I mean, it is becoming, the space is becoming huge and huge. But the problem is, what could be the problem if the number of bedrooms increase?
Maintaining
It
them.
becomes harder to maintain.
Right. So maintenance would be a problem, right? So accordingly, the membership will decrease, right? The membership value will decrease as the number of bedrooms increase. Similarly, even if the number of bedrooms decreases, it will be difficult to adjust in that house. Comfort level will be less. So depending on that, you can model your fuzzy set, right? You have to use the ordered pairs notation. Okay. So what you're doing is you have this number of bedrooms in the house, and maybe beyond 6 you are saying the membership is 0, right? So what you're doing is up to 6 you're giving some membership, and beyond that 7, 8, 9, 10 is having membership 0. Not considering 7, 8, 9, 10 at all. 7, 8, 9, 10 is having a membership 0 in this set, right? So that is how you do it. So it depends, like 4, now in this case, in this particular, it's subjective, I told you. So this is 4 comma 1, but 5 you reduce it. 8, 3 also you have reduced it, but 4, 5 could be 1, 1. It depends. Some person might give 4 and 5 as 1, 1. So likewise you have to model. So now that this is the ordered pairs notation, remember this is called as the ordered pairs notation. The original definition, that notation which stems from the definition, formal definition of a fuzzy set, that is called as ordered pairs notation. Okay. Next is using membership function. So using membership function, you have to represent real numbers considerably larger than 10. Okay. So how will you represent that? Considerably larger than 10, and it is real number. So whenever you are given with real value discourse, right, a continuous discourse, universe of discourse, so in that case it is better to represent using a mathematical function, the membership function, the graph, right? Whenever you have discrete values, then you go for ordered pairs. But whenever you have real values in the universe, then in that case you need to go for a graphical representation, which is a mathematical formula. So you use membership function as the notation. Okay. So how will the graph look like? Real numbers considerably larger than 10. Try to understand this statement. How will the graph look like? It will be the nature of the graph. So if you're trying to draw it, how will the graph look like? This is 10, say. Right? Real numbers are not larger than 10, but they're considerably larger than 10. Okay. So how will the graph look like?
It could be exponential, or it could start off from a value that's much larger than 10. So let's say we're considering 1000 to be much larger than 10. So we could say the function is whatever the function that you want to implement, something exponential perhaps, plus 1000. So even at the start, you could say it's much larger than 10.
Something like that, right? It will keep on increasing.
Right.
Yeah. So this is some kind of a graph like this, increasing graph, exponential. And so what we have done is beyond 10, we are giving very small values. So you're increasing the values to a very small extent. Or you can take some number which is far enough and start from there, start giving the values there. Okay. So, so I mean, this is very small. This rise is very small. The membership, very, very small, 0.0001, something like that. Okay. And then it starts increasing. Okay. So that is how you will represent it. So using some membership function. Next is the plus separator notation. So using the plus separator notation, it's instead of the comma, you use the plus, and there's a numerator denominator formula, a kind of a notation actually used here. So it's basically this. So membership divided by the element. I mean, that's not actually division, but it is just a notation. Okay. So the same example, if you go for the comfortable type of house for 4-person family, it will be something like this. Membership is written on top, and the element whose membership you want to find, that is written below the uh, division sign. So that is and the separator is plus, which is used. So this is one more notation, alternate notation, in which fuzzy sets are written. Okay. So 0.2 by 1, 0.5 by 2. It is not the other way around. Remember, membership is on top and the element is below. So this is one more notation which is used in literature. And then there are other notations. So instead of the comma, you put the plus. In the ordered pairs notation, it remains same. Only instead of comma, there is a plus. Okay. These are some notations which you will come across in different books. Okay. And then instead of the plus, you're putting the comma. In the plus separator notation, here, this could be a plus, this could be a comma. Similarly for ordered pairs, this could be a plus, this could be a comma. Okay. So these are the different notations that you have to use. You can use for representing fuzzy sets. So next, we move on to the concept of linguistic variables and linguistic values. Suppose that x is the variable age. X is a variable and it is defining age. Okay. Then this, we can define the fuzzy sets young, middle-aged, and old. Right? So what is this? What is the meaning of this term linguistic variable? So linguistic variable, age is a linguistic variable basically. And it can assume different linguistic values such as young, middle-aged, and old. So basically, linguistic variable, as the name suggests, is a variable which is represented by words in the natural language. Okay? A linguistic variable is a variable which comes from words in natural language. Okay? And these linguistic variables can have linguistic values, will have linguistic values. So whenever you are defining a fuzzy set, you first define what is known as a linguistic variable, and then these linguistic variables will have some values which are also in terms of natural language. The values are also in terms of natural language. More so in terms of description of this particular variable. So values will be like, for example, for age, it will be young, middle-aged, old. So if I say temperature, if I say the word temperature, temperature is a linguistic variable. And what will be the linguistic values for the linguistic variable temperature? They will not be actual values, they will be the terms from natural language, right? It will be
Yes,
hot,
ma'am.
cold, very hot, medium, normal temperature, something like that, very cold. Okay. So whenever you're defining a fuzzy set, you always define the fuzzy set in terms of linguistic variables and not the actual values. Okay. So the universe of discourse is totally covered by these MFs, or the membership functions. So MS for young, middle age, and old. And transition from one MF to another is smooth and gradual. So basically, what happens is whenever you are defining this, so later on when you actually design, go for controller design or a fuzzy knowledge based system. So in that case, so suppose you're defining age. So when you go for age, so you say that you're defining a fuzzy set young, middle aged, and old. Suppose these three fuzzy sets you're defining. So the fuzzy set young may will look like this, say, right? This is fuzzy set young. What about fuzzy set middle aged? Middle aged will start from here, right? Something like this. Okay. So the transition from one MF to another is smooth and gradual usually. So this is one MF. This middle age is some other MF, right? Membership function. So the transition from this MF to this MF will be smooth and gradual. So it will not be like this, that young ends here somewhere and then middle age will be here, totally disconnected, something like that. Okay. There'll be some overlap. So what will happen is some values, like from the universe of discourse. So this is the universe of discourse, X values. These are the X values, right? Some values, there'll be an overlap. So the values of X, which will be part of young, will also be part of middle age, but the membership will change. So for example, this data point here, right? This data point of X is having some membership here in young. Okay. And what is that membership? In middle age, it is 0, right? Similarly here, this particular data point is having some membership in young, and it is having some membership in, sorry, here. Yeah,
Middle.
it is having in young. So it is like gradually it is having a lesser and lesser membership in young, and the membership is increasing towards, as we are going towards middle age. Okay. So whenever you are designing a fuzzy inference system or a fuzzy knowledge based system, so in that case you will have such MFs which will be which will be spanning the entire universe that you define, but the transition from one MF to another will be gradual and smooth, will not be abrupt. Okay. So you will not have, I mean, you will almost never have something without any overlap. Okay. It depends on the context. Like, I mean, it depends, like if the fuzzy set middle age, or if you have only young and old, something like that, you might not give, I mean, you will not have any overlap then in that case, right? Young is like ending here. Beyond that, I mean, old, I'm starting at a later point. That is fine. But usually that is not the case. Usually it is not the case. You will have such MFs which will cover different parts of the universe. So it will not be that some MF is not covering any part of the universe. You're understanding? The universe is the entire X values, right? This entire range. Suppose it is ending here. Okay, age is ending here, 0 to say maybe 110, whatever. 110 is the highest age, right? This is age. These are the ages. So when you're trying to model age, some MF has to take care of each age. That is what I'm trying to say. If I have young, I have old, I should have middle aged. There should be no points which are left in between. There should be no points which are left in between. That is very important in designing, when you go for designing a fuzzy controller or a fuzzy knowledge based system. Okay. So this is about the concept of linguistic variables and how the MFs are characterized over a universe of discourse. Okay. So never always understand that linguistic variables are defined rather than the normal variables that you have. Okay, the normal variables will take the values of the real world, but whenever you're talking about in terms of fuzzy sets, then we're talking in terms of linguistic variables. Okay, linguistic variables will take linguistic values. So this you can use treat this as an exercise and actually try to model these. I'll leave this as homework to you. Just model these, try to model these fuzzy sets using the notations that were there earlier. Okay, when you're going for real value discourses like this and this, okay, these will be real valued universes, right? Real numbers close to 10 or high speeds for racing cars. So in these two cases, you should go for the membership functions, that notation. And for this case, integers, when we're talking about integers, then you should go for the other notations which are there, like the plus separator notation or the ordered pairs notation, right? The ordered pairs and plus separator, because they are discrete numbers, so you can model them easily. You can list them down in the list fashion. It will be difficult for to write the same in case of a real numbers, real number discourse. Okay, so try to model these also using the notations. Always remember that whenever you are modeling fuzzy sets, then in that case you have to mention what is the universe. You have to write your assumption that this is the universe that I'm considering, and over that universe only you are going to model the fuzzy set. That is important. Okay. Next, we will look at the different terminologies which are related to fuzzy sets. Okay. First is support of a fuzzy set. So the support of a fuzzy set is the set of all X where the membership is greater than 0. Okay. So whenever all those elements which belong to that set basically with some membership other than 0. Okay. So when we are actually defining a fuzzy set in terms of ordered pairs, then we are only writing the elements which are having some membership. Okay. So what will be the support of that fuzzy set? Suppose my fuzzy set is 1 comma 0.2, 2 comma 0.3, and 4 comma 0.7. Okay, this is my fuzzy set. What is the support of this fuzzy set? The support is a crisp set, which is nothing but the elements which belong to this set. That's it. The elements, not the membership. It's a crisp set. Okay. Support of a fuzzy set is a crisp set such that the membership of that set in the fuzzy set, membership of that element in the fuzzy set is non-zero. It's greater than 0. Okay. So,
Hello, ma'am.
yes.
So, ma'am, essentially, your support is they're just relevant inputs, right, for your fuzzy membership function,
Yes. Yes. So, if
the
you're
ones that
talking,
matter in the
yeah.
universe
So,
of inputs.
yes, yes, yes. So, only the ones that matter. Okay. So, if you're talking in terms of this MF, there's an MF like this. This is a fuzzy set, suppose. Okay. So, what will be the support of the fuzzy set? This region. All the elements, I mean, up till this point, right?
Yes, ma'am.
Before this point, right? All the X values up till this point, this range. Yeah. Next is core or nucleus. So, what is a core or nucleus? The core of a fuzzy set is those elements where the membership is exactly 1. The core or the nucleus of the fuzzy set is the x values where the membership is exactly 1. Okay, so what is the core of this fuzzy set A? That the fuzzy set A which I have listed here. What is the core of this fuzzy set?
It would be only the elements in the top line, like the upper line that you've drawn. Like
No,
that.
no, no,
Then which okay.
no, no, no. In this case, the core is actually empty because there is no element which is having a membership 1.
Ma'am, are you talking about the small function that you drew over there to explain, or are you talking about a
No,
tilde?
no. See, this is having membership 1. So in that case, for this particular graph that I've drawn,
Yes, ma'am.
this will be the core. But for this, there is no element with membership 1. So it
One.
is core is empty. Core is an empty set. It's a null set. Okay.
Yes, ma'am.
Normality. So a fuzzy set is normal if its core is non-empty. If the core is non-empty, then the fuzzy set is said to be a normal fuzzy set. Okay. So in this case, fuzzy set A is a subnormal fuzzy set. It is not a normal fuzzy set because the highest membership value is not 1. The highest membership value is 0.7. Right? For the fuzzy set A, the highest membership value is 0.7. That means the core is an empty set. Core is empty. And since the core is empty, it is a subnormal fuzzy set. Okay? So normality means if the fuzzy set is having highest membership 1, then it is a normal fuzzy set. Otherwise, it is subnormal. Are you getting it?
Yes, ma'am.
Okay. Next is a fuzzy singleton. Fuzzy singleton is a fuzzy set whose support is a single point in X with mu X is equal to 1. Okay. So what is the meaning of this statement? There is only one point in the fuzzy set.
There is only one ideal input to your fuzzy set. So, um,
Exactly. So I say exactly, I want to model the fuzzy set exactly 50 years old. I say exactly 50 years old. So in this case, what is the fuzzy set? I have only one element with membership 1, right? I have only one element with membership 1. Okay, so such a fuzzy set. So the support of this fuzzy set is basically 50. Okay. Okay. So such a fuzzy set which has exactly one element with this membership as 1 is called a fuzzy singleton. Okay. Now fuzzy singletons are useful in some scenarios when you're modeling. So modeling these fuzzy controllers. In some scenarios, it is not possible to represent the set as a fuzzy set. I mean, you do not have a collection of values. You have some, some anomalies, or you can say you have some certain values which have to be modeled in this fashion. But still, you're using fuzzy logic. You're not using classical set theory, right? You're representing it everything using fuzzy logic. But because of this one outlier that you have to represent, you still have to use fuzzy logic now in that case. So such sets are fuzzy singleton, single element with membership 1. You have to have, there are certain scenarios. In fact, we have used this in one such controller that we had designed. Actually, I have a research paper on that. I'll definitely show that to you where we have used this. Okay, so this particular scenario where you require, sometimes you require to model it, you have a single element with membership one, that is a fuzzy singleton. And fuzzy singletons you will also see in the design of fuzzy controllers somewhere in Sugano inferencing. Okay, so we will talk about that later when we talk about inferencing, fuzzy inference system. So fuzzy singleton is still some scenarios you require fuzzy singletons. So next terminology, alpha cut. What is this alpha cut? Alpha cut is a crisp set which is a set of all x such that the membership of this x inside A is greater than or equal to alpha. Okay, so alpha basically is a membership value. Alpha that we're talking about is a membership value. Okay, so if I talk about this particular fuzzy set that we had defined, I can this A. Okay, so what is A point 2? What is A point 2? That is A alpha. I have written alpha cut as A alpha, right? Where alpha is 0.2. What is A point 2? It says that it is the set of all elements which belong to A which have a membership greater than or equal to alpha, right? Which have membership greater than or equal to alpha. Yes or no? It's the definition. So what is this alpha cut? What is this alpha cut? A point 2 with respect to this set. It is 1, 2, and 4. Okay. What is A point 3? What is A
2 and
point
4.
3? 2 and 4. Okay. That is how you define alpha cuts. So they are also useful. This is a useful thing. Later on, we'll see for some concepts where alpha cut is used. So A point 2, A point 3, A point 7 is 4. And then there is, if I say A1, membership 1, it is null set, right? 0.2, 0.3, 0.7. Okay. So that is what is alpha cut. Similar to alpha cut, you have strong alpha cut. Okay. Strong alpha cut has this condition, stricter condition, that is strictly greater than alpha. The membership value of that element should be strictly greater than alpha. That is strong alpha cut. So you have alpha cut and you have strong alpha cut. Okay. Only difference is strong alpha means that greater than equal to sign is strictly greater than in case of strong alpha. Okay, so all these are alpha cut and strong alpha cut. These are crisp sets defined from the fuzzy sets. Okay, of only the elements. We are talking only of the elements. The x values we are looking at. One more thing is alpha cut is also known as alpha level set. Alpha cut or alpha level set. Okay. Alpha cut, alpha level. It's a level. Beyond that level, you are finding out all the elements. Beyond that level. So strong alpha cut, strong alpha level set. Then you have cardinality. What is the cardinality of a classical set? What is the cardinality of a classical set?
The size of
Number
the
of
set.
elements in that.
Number. Number of elements of a set. It's cardinality. Okay. In case of a fuzzy set, the cardinality is equal to the sum of the membership values of all elements. The cardinality is equal to the sum of the membership values of all elements of the set. That is what the definition is. And there is one more definition called as relative cardinality. So what is relative cardinality? Relative cardinality is equal to the cardinality of the fuzzy set divided by the cardinality of the universe. Okay. So cardinality, understand, for a fuzzy set is equal to the sum of the membership values of all the elements of the fuzzy set, and relative cardinality is equal to the cardinality of the fuzzy set divided by the cardinality of the universe over which it is defined. Okay. Next is height of a fuzzy set. The height, what is the height of a fuzzy set? Height is equal to the largest membership degree. The largest membership degree of the fuzzy set is nothing but the height of the fuzzy set. Okay. If the height is equal to 1, then the fuzzy set is normal. If the height is less than 1, then it is subnormal. Okay. So if you know that the height of a fuzzy set is 1, it is a normal fuzzy set. Okay. So you can also define a normal fuzzy set in terms of height. Alternate definitions. So as an exercise, you have to find out for these particular fuzzy sets, what are the alpha level and strong alpha level sets. Okay. And also, so you'll be able to find for this particular fuzzy set, alpha level and strong alpha level set. It's pretty simple. You only have to look at these membership values which are given 0.1, 0.2, 0.3, 0.4, 0.6, 0.8, and 1. Okay, and list down all the elements. So how many alpha sets will come here? So you will have A, suppose A is this set, let me call this as A. If A is this fuzzy set, then you will have to find out A.1, A.2. This is for alpha level sets. What was the notation for strong alpha level set? I mentioned it. It is A dash, okay, A alpha dash. This is the notation, A alpha dash. So if A.1 is, what will it be? It will be 3, 4, 5, 6, 7, 8, 10, 12, all elements, right? What will be A dash 0.1? This will not come.
Everything
Right?
except 3.
Everything except 3. Wherever there's 0.1, that you don't have to take. Right? A.2. So similarly, so one element will, 1 or 2 depends how many elements are having that membership. So for example, when I talk about A.8, when I say A.8, then what is it?
8, 10, 12.
8, 10, and 12. But what is A dash 0.8?
10.
Only 10. You're getting it? How to compute? And A1 and A dash 1. A dash 1 is a null set.
Null set.
That's it. So this is how you find out alpha level and strong alpha level sets. And all the other terminology you can actually find out. So what is the, whether this is this a normal fuzzy set? Is this
Yes.
fuzzy set A? Yes. Okay. So what else? What else did we discuss? What is the core of this fuzzy set? What is the core? What is the core of the fuzzy set?
10.
10. What is the support of the fuzzy set?
All the numbers.
All the elements. Okay. So likewise, you can, what else did we miss? What is the cardinality of this fuzzy set? Sum of all membership values, right? Sum of all membership values. So just add up everything together. What is the relative cardinality? When the universe is not given, when the fuzzy set is directly given like this, you assume the universe with of containing these elements only. Okay, if it is not given, usually that has to be given in order to find the things, the terms and all those definitions, right? So if it is not given, assume and write your assumption that the universe is 3, 4, 5, 6, 7, 8, 9, 10, 12, 14. So cardinality, relative cardinality also is sorted. So if you're assuming this as the universe, all these elements only as the universe, then 1, 2, 3, 4, 5, 6, 7, 8, 9. So divide whatever is the sum of all those membership values, right? What is relative cardinality of fuzzy set A? It is cardinality of A divided by cardinality of X, right? So cardinality of this is all a summation of all the membership values of X or of A, and this is equal to the number of elements of X. Cardinality of X is equal to the number of elements. So divide by 9. Whatever sum you are getting, divide by 9. That is the relative cardinality of fuzzy set A. Is this clear?
Yes.
Okay. Operations on fuzzy sets. These are the operations: containment operation or subset operation. So what is containment? Two batches have already done their practical. So where we have started with this, where we discussed the operations. So containment or subset is the definition is this, that all the membership values of A should be less than or equal to the membership values of B. Then in that case, A is said to be contained in B, or A is said to be a subset of set B, fuzzy set B. Okay. Second is intersection, union or disjunction. So in that case, in the case of union, we find out the max between A and B. Max of the membership
Membership.
values of the element X in A and B, right? Intersection is the min. Instead of max, you use min. Okay. So whenever you are performing these operations, we are talking with respect to two fuzzy sets, A and B. So A union B is combining the sets into a single set, right? Similarly, intersection. What is complement? Complement is 1 minus the membership of that element in A. Okay. So
Respect to the universe of discourse.
yes, with respect to the universe of discourse. So next we move on to the properties. I mean, the examples are there. We'll just discuss the examples. Just let me list down the properties. So these are the properties of fuzzy sets, which are similar on similar lines with classical sets. So A union B is commutative, A intersection B is commutative. Associative are union and intersection. Similarly, you have distributivity. It's the same. Okay. Then you have this identity. A union null set is equal to A. A union universe is equal to universe. Okay. A intersection null set is equal to null set. What is missing here? What is missing? Rest all it was there in case of classical sets also. What is missing? You remember law excluded middle, law of excluded middle. Law of excluded middle. Law of excluded middle. What is law of excluded middle? In case of In case of a classical set, A union A complement, what is it equal to?
X.
X. And what is law of contradiction?
A intersection A complement is equal to null.
Is this true? Are these laws true in case of fuzzy sets? Okay, let us see. Let us take one example, simple example, very small example. A is 1, 0.3. Okay. Assume universe is 1, 2. Okay. Now, what is A complement? Using the intersection notation, A complement. Sorry, the complement definition of fuzzy set. What is A complement? A complement. Whatever is a membership, 1 minus that. Do you remember? I had just given you this. Complement or negation is 1 minus membership. So what is A complement?
1, 0.7 and 2, 0.4.
1, 0.7 and 2, 0.4. Okay. What is A union A complement now? Will it be equal to X?
No.
No. Why? Because this is having some membership, this is having some membership. And union is the max of the two memberships. So you will get 1, 0.7 and 2, 0.6. Yes or no? This will be A union A complement. Okay. But what are you expecting? You are expecting 1, 1 and 2, 1. That is X. If I write 1 with membership 1 and 2 with membership 1, then that is same as X. Yes or no? Okay.
Yes, ma'am.
So A union A complement in the case of fuzzy sets will not be equal to X. And likewise, if I do the other thing, other operation, that is A intersection A complement, again I am not going to get the null set. Yes or no? I will not get the null set. I'll get the minimum value. In case of A intersection A complement, I'll get the minimum value, 1 with 0.3, 2 with 0.4. Right? I'm never going to get the null set because null set will be all 1 with 0 and 2 with 0, membership 0, null set. Right? So these two laws don't hold in case of fuzzy sets. These two laws of classical set theory do not hold in case of fuzzy sets. Is this clear?
Yes, ma'am.
Okay, so now there's one more exercise. You have to perform all the standard operations and verify the De Morgan's laws. So this you can do as homework. Again, these two examples, or you want me to discuss? You want me to
No, we'll do
discuss?
it. We can do it.
You can try this, right? Everyone else, those who have not had practicals, it is okay. If you want that explanation in your lab, definitely I will give that. But I think you can practice this then. Simple union, intersection, and De Morgan's laws. Because such kind of problems could be asked for 2 marks or something like that in the exam. Or some kind of an application where you have to use it. Right? Everyone, this is clear? Union, intersection, De Morgan's. All these laws, properties are clear. Operations are clear. Only thing you'll have to practice it on the set, the example. Fine?
Yes, ma'am.
So we will stop here for today. The next lecture will continue with more such terminologies. And we will extend the discussion before we actually talk about design of fuzzy control.